Let's see how this records. All right. So we went through, talked about logistic models, categorical data, odds. I'll start right here. Just as a recap, it's going to be a weird thing here. I guess I'll laser this. Maybe that'll show up on the video. So with our logistic models, remember what we're doing is we're regressing a dichotomous outcome variable, well, a categorical outcome variable. Here we're working with just a binary logistic model where we've got a dichotomous outcome that we're looking to regress onto a series of categorical and continuous predictors. Okay, but what we're probably looking at is wanting to regress a probability, right? What we want to know is what's the probability of this outcome or what have you, right? But remember, problem is probability functions aren't linear functions, right? They have this kind of S-curve business going on, and it's also bounded by 0 and 1, right? You can't have a probability over 1. You can't have a probability less than 0. And so as you get closer and closer to those boundary values, you see this asymptotic curve there, right? And so the problem is that we can't, with our general linear models, regress a linear model onto a nonlinear outcome because it's not going to be a good fit, right? And so what we end up doing is we end up sort of taking this probability function, and we can get linearity in these parameters, right? But what we end up being is, if we're want to predict a probability, what we end up is base e to our linear function over the top of 1 plus base e to the linear function. That's a nasty, nasty mess, right? So we still have our linear model in there, it's just in a weird proportion. And so what we do, though, is because our probability is nonlinear in its parameters, what we can do, though, is we can transform that nonlinear function so that we can create, sort of estimate a linear model that then we're predicting the linear transform of this probability function outcome. And a lot of different link functions that you'll see different types of probits and things like that. Depending on what type of data you're looking at, you may use a different link function. But the most common function that we see is the regression of a logit or a log odds. And so basically, if this is the probability function that we're trying to predict, we can't do that easily within our basic general linear model. But what we can do is we can transform this and solve for just the linear equation. And what we get here, at least in the natural log or in the most standard form, is a linear model that's predicting the natural log of an odds ratio, okay? And so what we do with our logistic models is we're predicting not our probability outcome. That's what we wanted, but we can't get there. But what we can do is we can take that outcome, that 0-1 outcome, and go through, translate it into the natural log of an odds ratio, so the odds of an event versus the odds of a non-event. And what ends up happening is then we can use this logit or log odds and predict that with our general linear model, okay? So here you can see linear regression equation on this end, predicting the natural log of the probability of being in one group versus the probability of it being in a different group, okay? So we've got a log odds going on here. Our logit or our log odds is linear in its parameters, okay? So it can be 0 to infinity, okay? Or no, negative infinity to infinity, right? So natural log of your odds is linear in its parameters. It's continuous. What we're doing is determining the odds of being in a particular category versus another, given a set of predictors. But the thing is, remember that this is going to be different than our standard regression model, where our regression equation predicts our outcome, right? In our logistic model, our regression equation isn't predicting the outcome. Our regression equation is predicting the natural log of the odds of being in category A versus category B, which adds a little bit of complexity to this, but it's not anything that we can handle. as long as we know what we've got going on with this stuff, okay? Questions on sort of how this model is set up, what we're doing, and why we have to set it up this way? Feeling good about this? Okay, cool. So again, we had talked about maximum likelihood estimation, sort of some of the stuff there, a demonstration about maximum likelihood, how that's working, right? So jumping into our example, okay? Let's say, and if we look at have a binary logistic model, this is looking at an outcome that just has a dichotomous sort of either it happened or it didn't, right? Now we can get into more elaborate models where we have multiple categories, right? So we have, so you can be in category 1, category 2, or category 3 as your outcome. Refer to these as multinomial logistic models. But at the end of the day, what you're still doing is you're still sort of breaking that down into a binary logistic model, because what you end up doing with that is you have a series of models that are predicting sort of some outcome versus a reference group, right? So if I have 3 outcomes in the multinomial, right, I can't predict the probability of sort of all of these 3 together. What I end up with 2 models that either predicts the outcome of B versus A or C versus A, and so again we have to have some sort of reference group with that. Now I've given you a handout that goes through an example of a multinomial logistic regression. You can take a look at that if this is something that ends up coming up in the course of your research. You can go through Reed, Tabachik, and Fidel. Would strongly recommend that you do that anyway, but we won't worry about multinomial models here just because we don't have enough time. But for our binary logistic regression, we're looking at an outcome that takes on 2 values, 0, 1. And the purpose of the model, predict the odds of falling into some criterion category relative to a reference category based on our best linear combination of independent variables, okay? And so, again, this is one of the things that becomes crucial, I can't emphasize this enough, as you're going through, you're talking about and going through and interpreting your coefficients in these models, absolutely need to know what category or what level of your categorical outcome is your reference group versus your criterion, okay? Anytime you sit down with this, because SPSS does some things that are not intuitive, always want to make sure, whether it's for your outcome variable or for your predictors, know what the reference group is, what your criterion group is, so that you're interpreting these appropriately. Because if you get that screwed up, you're going to get some funky answers that hopefully you catch and go back through and take a look at that. And when we go through the output, we'll look at sort of how you can go through and check and make sure you know which group is which, because it's going to be important for moving forward with some of this stuff. So, example, I can't remember if this might be Tabachik and Fidel, I can't remember. But let's say we have a small model where we want to assess the probability of falling on a ski trail based on difficulty and what season we're talking about, okay? The idea being that we've got a level of difficulty assessed on what we'll call a continuous variable. It's actually not, it's just 3 levels, so this is ordered categorical. This is another thing to be mindful of what your variables are. I mean, this is, for this example, fine, we'll treat this as continuous, but if I were actually putting together a publication, I would be very hesitant to call 1, 2, or 3 and treat that as a continuous variable. There are alterations and sort of variations on this model that you can go through and account for ordered categorical IVs. But then we also have season, right? Season, this is a true categorical outcome. There's no, I mean, time-wise, there's a progression, there's an order to it, right? But there's no sort of meaningful sort of quantitative difference between these two. So in this example, we've got 1 is autumn, 2 is winter, 3 is spring. And in this case, spring, that you'll see the asterisk there, this is our reference group, okay? And so we'll end up modeling this as our, kind of like an indicator regression, where our impact of season will be, our specific effects will be comparing autumn versus spring, winter versus spring, and spring being our criterion group. So the model that we estimate, and here's our data, right? Skiers 1 to 15, whether or not they fell, difficulty of the trail, and what season it was, right? We have our estimated model. What we're doing, and when we run this logistic model, this is our regression equation. This is our regression equation we know and love and have spent so much time with, but our outcome here is not the probability of falling or not falling, right? Our outcome here is the natural log of the odds of falling versus not falling, okay? But what we can do, given this equation, and given what we know how to get into that, how this relates to probabilities, we can, just like for a regression equation, if I want to have a predicted score for Trent, right, and I want to see what Trent's, my model predicts Trent's score is for some continuous outcome. Same thing, we can do this here. If Trent is skier number 1, I can take this model, this regression equation, and sort of back translate it into and actually get a probability for Trent, right? Basically what we do, given that we know sort of this relationship here, right? What we end up doing is we can take the coefficients from this model, right, and plug them in and take e to the sort of whatever my linear function is over the top of 1 minus e to the linear function, plugging in the season and difficulty for Trent to determine the probability that Trent falls on this ski slope. Okay. So what's up?
Probability of me falling is very high.
Well, so I don't know. We'll see. Depending on the trail difficulty, things like that, we might get different answers here, right? Okay. So, but recognize that this is the model that we're estimating, but we can still take those coefficients, translate them back in to actually get a specific probability for any individual in our sample, just like we would do with a normal regression equation, right? What it ends up being is we just take base e to the regression equation with our variables punched in here and take that over 1 plus base e to sort of whatever our model is there. Okay, and so you'll see we have a coefficient, we have an intercept, we have a coefficient for difficulty because that was our continuous variable, and then we have 2 dummy codes for season. Candace, what do these dummy codes represent within the context of this model?
It's going to be fall. Spring is the reference group, so the dummy codes are going to represent autumn and winter.
Versus
spring.
Right. So we'll have, this is a coefficient that tells us the increase or decrease in the odds of the natural log of all falling versus not falling for autumn relative to spring, and this one will be winter relative to spring. So model fit for logistic models, right? So thinking about, we want to have some tests of whether or not our model is actually doing anything, right? Similar to analog being our R squared for our continuous regression models. Model fit with our logistic models determined by a log likelihood, where our log likelihood is the sum of our actual outcome times the natural log of our predicted outcome plus 1 minus our outcome times the natural log of 1 minus our predicted outcome, okay? This is just how this is calculated. This is what this looks like in practice for our skier data, right? Here's our list for each of our individuals, whether or not they fell or didn't fall, right? What we do, what SPSS is doing in the guts in the background, is it's taking that and taking that against our predicted value of whether or not a person falls or not falls, right? And this is 1 minus that estimated value. Then we have our actual outcome times the natural log of our predicted value. Here we have 1 minus our outcome times the natural log of our predicted value, and then we get our log likelihood value here, okay? Well, what you'll notice is depending on sort of whether or not someone fell or didn't fall, if they didn't fall, y times the natural log of our outcome is going to be a number, but here this is going to reduce to 0 because 1 minus 1 is our actual outcome, is 0, and we multiply 0 by anything, and then that goes away, right? Mm-hmm. For people who didn't fall, we don't get a value for y times the natural log of our expected outcome because our expected outcome is 0. We put 0 there, right? And so we get across these two, depending on whether or not the person fell or didn't fall, we get a value here, and we'll see here for someone who did fall. And for this person, it looks like we did a pretty good job of predicting whether or not they would fall, right? So 1 minus our expected value is something quite small, and so when we take 1 times our natural log of our small number here, we get a log likelihood value that's quite small, versus the second case where we're predicting this person fell. If we use 50% as our tipping point, right, we would classify this as a fall, and we did it correctly, right? But the problem is that when we take 1 minus this, we get a larger number. When we take 1 times the natural log of this predicted outcome here, it's a much larger log likelihood than this, right? And so what we end up seeing is that our lower log likelihoods indicate better model fits, right? Because if our model is doing a good job, this estimated value should be very close to 1 or very close to 0, right? If it's right around 50%, then we get a 50-50 thing, then we're starting to get worse off, right? And then we get outcomes like this where our model predicts that a person didn't fall, but they did fall, right? And we're getting larger log likelihoods here. So what we do is we set up this table, add up some of the log likelihoods, and we get a model log likelihood for the whole thing, which is the sum of the individual log likelihoods for our individual cases. Our model log likelihood can be multiplied by -2 to place it on the chi-square distribution. Why -2? Or why negative? Maybe not 2. I don't know the answer. Why 2? But why a negative? Why are we multiplying it by a negative number? To make it positive, right? We have negative chi-square values, right? Chi-square distribution is all positive. But if we multiply our log likelihood by -2, we get a -2 log likelihood. Lower values indicating better fits. And what we can do with this is, if we have nested models, what we can do is we can start subtracting the difference between -2 log likelihood against a base model, and we can start looking at whether or not we have a better model given the inclusion of some variables versus without. A significant chi-square indicates reliable improvement in the overall model. Yeah.
I don't really understand what a nested model is.
Nested model, let's say I've got, for example, let's say, like, going back to moderation, right? So I've got a model with 3 direct effects, right, or 3 first-order effects, and then 2 interactions, right? My model with the 2 interaction effects, or the model with just my 3 first-order effects, is nested within my model with all 5, right?
Oh.
And so what we can start doing is we can say, and we'll see this is how we calculate this, is you'll have what SPSS will do is it'll estimate a baseline model and says, what's the fit if we just don't have any predictors in here? And then what you'll do is it'll compare that against your full model with all the predictors, and the baseline, the independent, or the model that has no predictors in it, is a nested model in with the model with your full predictors. And what you can do is you can look at the chi-square, or the -2 log likelihood of the model with just no predictors in it, and compare that against the -2 log likelihood of the model with all your predictors in it. And what you're hoping to see is a reliable decrease, right? You're looking at hoping to find that difference in those 2 log likelihoods is distributed on a chi-square, with the degrees of freedom being sort of the number of extra parameters in the base model versus the full model. And what we can then do is start to, so if we say, if I had a continuous or a dichotomous outcome, I might test my full model with my 2 interaction variables in there, and then I would estimate a base model with just the 3 direct effects, the 3 first-order effects, and then what I would do is I would take the -2 log likelihood from the model with all 5 predictors and compare that with the -2 log likelihood of the model with just the 3 predictors, and if the difference between those 2 log likelihoods exceeds a critical value for chi-square with 2 degrees of freedom, then we would say, yes, it looks like the inclusion of these interaction terms has produced a reliable increase in the overall quality of this model, right? So this is a lot what we'll do. So this is the reason we're going through, not that I'm going to have you go through and calculate this out, but understanding what the log likelihood is It's just a broad index of model fit. Lower values are better, and we're going to use this flexibly to go through and test individual predictors and different types of models and things along those lines. Okay, does that help?
Mm-hmm.
Any other questions about this? All right. So another thing